Hi there everyone. In this video we're going to look at the differentiation of the exponential function. And just as a little intro, I'm just going to sketch a couple of graphs. So I'll start by sketching a graph and we'll call it 3 to the power of x. Now it so happens that if you differentiate that graph, the gradient turns out to be steeper than the graph itself. And so when you graph the derivative function, you get another graph that's steeper. Now let's consider another graph, and I'll call this one the graph of 2 to the power of x. And when you differentiate that graph, it turns out its gradient function is less steep, and so it's a curve that's underneath. Now we've got this sort of Goldilocks function where you have the function, the curve. We'll call it e to the power of x, and the special thing about this curve is when you differentiate it, it differentiates straight to itself, and that's what we're going to look at proving. So you might have seen me do this in class, but we're going to do it here very quickly anyway, and we're going to look at the function e to the x and what it differentiates to using first principles. So we're going to have to work out the function of x plus h, which will be e to the power of x plus h. And we're going to substitute this into our first principles formula. So f dash of x is the limit as h tends to 0 of f of x plus h, so that's e to the power of x plus h, minus e to the power of x all over h. Okay. And so what we're going to do is factorize this. Just as a side note here, e to the x plus h, that's the same as e to the power of x times e to the power of h. And so I'm going to factorize out my e's, and so I'm going to have e to the power of x times e to the power of h minus 1, and that's all over h. And so you can see here that we've got e to the power of x by itself, and that's not directly affected by h in any way, so we can kind of factorize that out of the limit if you like. So what I'm going to do is write it as e to the power of x of times the limit as h tends to 0 of everything else, so e to the h minus 1 over h. Now this function here, now that it's just got h's in it, we can evaluate that limit. So we'll draw a little table here where we've got values of h, and we'll go, because we're evaluating a limit close to 0, we'll start with 0.1 and then we'll progressively get smaller. Okay, and we'll evaluate the function e to the h minus 1, that should be a big minus 1 all over h. So let's put in 0.1 and see what we get. Okay, so we've got e to the power of 0.1 minus 1, and that all divided by 0.1. So we get 1.05. Okay, let's try that again and just put in an extra 0 for our substitution of h, and we get 1.005. I'm willing to bet that our calculator will give us this for our next one, but let's just double check to make sure we're not making too many assumptions here. Okay, and indeed it does. So what we're seeing here is that this whole function is tending to 1 as we take the limit, and that is indeed the case. That whole limit there equals 1, and therefore we can say that the derivative is equal to e to the power of x. Okay, so that's our proof of the exponential function. In my next video I'm going to look at these two examples here.